Okay, so with the last couple of pages, we've talked about a kind of permutation, factorial, and then permutations where we did the NPR. And in both of those cases, we could not have repetition. Repetition was not allowed, and also order mattered. So in this particular video, we're going to talk about combinations. In this case, order doesn't matter. And let's develop that just a little bit. So example 22. For each scenario, decide whether or not the order in which the selection is made matters. Now remember, we were mentioning that you need to use your common sense a little bit here when we determine whether or not order matters. So you order a 4-topping pizza. So if you think about it, when you order a pizza with a different number of toppings, it doesn't matter which topping you say first. All those ingredients are going to get mixed up on the top of the pizza anyway. So in this case, order does not matter. You create the 5-digit code for your garage door. Now, as you're looking at using these digits, it does matter what order you enter those digits, or else your garage door will not go up. So order matters. Three people are given a raise at work. One gets an additional 15 cents an hour, one gets 25 cents an hour, and one gets 35 cents an hour. Well, if I were those employees, I would care which one of those I got. They're all different, so order matters. But on D, you'll see that they're all given exactly the same thing. So order doesn't matter in that case. It doesn't really matter in which order you award those raises. Combinations. In the previous example, you notice a few scenarios where the order was not important. Let's look at what this does to the number of possible outcomes. I'm going to move this up just a bit here. Let's take a look at 3 people, call them A, B, and C, who all get a raise at work. If they all get a raise for a different amount of money, in how many ways can that happen? Well, if you don't mind, I'm going to go ahead and list how that can happen. Let's say they happen in the order of A, B, C. Well, how about A, C, B? Well, perhaps A did not get that first raise, so let's put B first. So that'd be BAC or BCA. All right, that's all the situations where B got that first raise. And so let's say C got the first raise, so CAB or CBA. That's what it looks like when order matters, right? And so that can happen 6 different ways. But what if they all get the same raise, and how many ways can that happen? Well, just one way. It doesn't really matter what order, does it? All right, so the other question is, how does the number of outcomes when order matters compare to the number of outcomes when order doesn't? Well, it looks like when order matters, I would have to say most of the time, your number of outcomes is bigger. I would have to say when it counts. I am going to go ahead and have us compare what the combinations look like and the permutations look like as far as what our answers look like. And I think it's just a good idea to get practice with it anyway. And so sometimes we have to do some pretty complicated computations. So it's nice to have an idea in our mind what the answers would be. So I'm going to write these down real quickly. Okay, I figured in both cases let's use 5 choices. So you'll look at when order doesn't matter, you only have one way that that can happen. When order does matter, if you have 5 items, you have 120 ways that that can happen if order matters. Okay, and so I think you can see the comparison there. So let's look at these. Now think about it. You only have one item that you're taking from your 5 choices. And if there's only one item that you're taking, there's nothing to order, is there? So it really doesn't make a difference at all whether or not we use combinations or permutations. So I just wanted to point that out real quickly. And looking at our formal definition, there are NCR, combinations of size R, that may be selected from among n choices. So I would like to point out to you that if we just look at the numerator and this part right here, it looks like permutations. So what's up with this right here? The R factorial will take care of the fact that when order doesn't matter, remember our example with the raises? ABC is the same thing as CBA, okay? So in permutations, those are 2 different outcomes, and in combinations, we don't really differentiate between the two. So that will take care of all those repetitions for us. All right, so combinations are used in situations where there is, again, no repetition. And the order of selection does not matter. Okay, let's do a couple of quick examples. A group of 4 students is chosen from a class of 25 to pass out art supplies to their classmates. How many ways can this be done? So it is the same job. Okay, of course, the one student can't be doing the job of all 4 kids, right? So you have to have 4 different kids, no repetition. But it's not like you're celebrating because you are art supply passer outer number 1 or art supply passer outer number 2. So those are all the same job. So that's an example of a combination. So 25C4, put that in our calculator, we get 12,650. B, you order a 3-topping pizza from your favorite restaurant. You order 3 different toppings from a list of 17 available toppings. How many different pizzas could you order? So again, in most places, they just throw the toppings on top of the pizza. You're not going to say to the waiter, I did not order mushroom, sausage, and onion. I ordered onion, sausage, and mushroom. What's wrong with you? No, those are all the same thing. So that's another situation where order doesn't matter. We're going to assume that you're not going to order double toppings here. Okay, so 17C3 gives us 680 ways that that can happen. Should probably put the ways up here too.